Hi there, Bob Nagy, AB5N, back with a very interesting radio today, and it's a Xiegu G-90. Now, Xiegu is a very small Chinese company that has been entering the amateur radio market with a bunch of QRP radios that you probably have seen out there. They also produce a matching amplifier, which I recently reviewed, so if you want to take a quick look at that. The G-90 is a new radio in their G series, they call it, and it's a miniature QRP portable SDR radio that covers 160 to 10 meters. Does not cover 6 meters, but covers those primary bands in almost all of the modes. It's the first in their new G series of radios, so I'm not sure if that means that they're all going to be SDRs or what it is, but this is a very interesting and quite different radio. So let's dive right in and take a look at the radio first physically, and then get into all the features and functions of the radio. Now, there are other SDR QRP radios like the amazing KX3 from Elecraft in California. I own it, I love it, and also the MCHF out of the United Kingdom, a great SDR portable QRP radio. The thing that sets the G90 apart is that it uses a 24-bit A to D converter IC, and that's next generation. It's not a direct sampling SDR such as the Flex radios and the ICOM 7610. It's a mixer type SDR. That means it mixes the RF down to a lower frequency and then samples with a to D chip. In this case, the Cirrus Logic CS4272 24-bit A to D IC running at 48 kilohertz. It's small, but it's no slouch. Now I'm going to add my little 13-minute SDR primer, because a lot of guys out there are still a little bit unclear on SDR concepts. So if you know all this stuff, go ahead and skip to around minute 15 or so and continue on with the video. Those of you who want to get a handle on SDR technology, keep watching. Well, we remember the old super heterodyne radio, the RF amplifiers, the local oscillators, mixing different IF frequencies, and then finally detecting the information off the signal and providing that audio to an audio amplifier. With an SDR, the A to D chip, or called the ADC, is the first thing that the RF is really going to be dealing with. And these are rated in bits. We might have an 8-bit, 12-bit, or 14-bit, or even more, and a sampling frequency. And this is really going to do the primary determination of the overall quality of the receiver. It's important to know that an ADC chip, analog to digital converter chip's dynamic range, is primarily based on the number of bits. And that basic dynamic range of the ADC chip is a function of how finely that analog sample that it's digitizing can be sliced up and represented. With less bits, there's more digitizing noise. And of course, we're trying to get clean digitizing from the smallest to largest signal. So as you see on the bottom, as we go up in bits, the dynamic range calculation goes up dramatically. The first generation of SDRs were what's called mixing or quadrature mixer SDRs. The A to D chips were not fast enough to really directly sample the RF. So we had to do a little bit of mixing to move it up to a situation where these earlier A to D chips could handle the data and information. The G90 is using a lower cost and lower speed A to D chip, but it is at 24 bits. Recently, A to D chips have become so fast and so high-powered that they're able to directly sample RF with a little bit of bandpass filtering and such before them, but they're getting much closer to just looking right at the RF itself. Let's look quickly at exactly how the signal gets through a direct sampling SDR receiver. Coming in the antenna, we go through the bandpass filters on most radios, can be broadcast filters as well, or pre-selection filters for the amateur band, then to that famous A to D chip that we talk so much about. And it's going to go ahead and sample all of the RF world and convert it into a digital bit stream that goes into the field programmable gate array. And the FPGA actually sort of emulates some of the old analog functions in converting that digital data into a format that can be sent to the DSP chip that it can deal with and understand and be able to use. So it comes out in digital form, all this still happening in the digital domain out of the FPGA into the DSP chip. And we're going to see the DSP do all the demodulation of the different modes, the noise reduction, the filtering, the notch filtering, emulating all of the analog world filtering and demodulation, and then splitting it, sending it over to the D to A converter, because it's still in the digital domain, converting it to audio stream. Actually, there's usually an audio amplifier after that, and goes to your speaker. You saw it also branch off the FPGA to the display processing for giving you all of your spectral displays and that kind of stuff. In the new FTDX 101 Delta, you can select a direct sampling mode or a mixer mode for tighter bandwidth control. On the transmit side, we're seeing the mic audio coming in through an A to D converter chip to digitize the incoming audio, then going through the DSP processor, which does all that simulation of the modes, FM, AM, sideband, that kind of thing, sends that digital signal to the FPGA, that gate array, which does those pseudo-analog frequency shifting things and actually generates the appropriate signal, and that needs to be converted to analog in the next chip, which is the D to A center there. That's going to be bandpass filtered after that. Now we're dealing with an analog signal. We've got the ALC, which is working for us to give our levels right, PA amplifier, low-pass filter, and out the antenna. Getting closer to sampling that RF directly, using less components between it and you, between the RF and the AF, is going to result in necessarily a higher fidelity reproduction in the entire system, because all through the ages we've been trying to fix image problems and other things by adding another LO and shifting the frequency here or there. And every time you do add another one of these sections, you add another potential problem area. You don't get something for nothing. So we got up from single conversion all the way to quad conversion receivers. But really, if you strip it down to basics and get into the digital domain and get to a direct sampling SDR, you've taken it right down to the direct relationship with the RF, and you can land up with a much better fidelity. I'm calling it fidelity. Basically, it's linearity and fidelity throughout the system, resulting in a cleaner transmit and receive signal. Now, what's happened is a lot of folks out there, especially Adam Farson, who's driving this, is re-looking at how to test SDRs, because a lot of the classic tests that we used in the past are no longer applicable to an SDR. And the number one that comes to mind is IP3, the third intercept point, because, boy, that was the number. The manufacturers would advertise their radios, so it's got a plus 30 or it's got a plus 40. But in an SDR, it just doesn't have a lot of meaning, because what you're looking at is how much of an interfering signal is required nearby you to create problems for you in the passband that you're looking for, or you're looking at. And with an SDR, that interfering signal starts coming up, but then all of a sudden it just plateaus and drops out, and there's the two lines never meet, as you can see in the charts here. So that has to be replaced with something else. Now, there are tests that still make sense for both types of receivers, a legacy, traditional superhat, or a blend of, and an SDR, and that's the minimum discernible signal, MDS. We want to know, how low can we go and still receive a signal down there in the noise. RMDR, which is a reciprocal mixing dynamic range, this is going to be a lot more important with the SDRs now. So you're going to see that spec really sort of come up. We do still have intermodulation products, distortion products creeping up, so you're going to see that as well. But also in the SDR, there's no DR3, or DR3 doesn't really make sense to use in an SDR. So you're going to see the focus come away from the classic numbers onto some other numbers. Some of them still in common, but some of them now they're going to have a heavier weighting and some new tests to look at SDRs. You might look at Adam Farson, VA70J, AB40J, his writings, because he is leading the trail on this. Two tests that I think you will start to see showing up to test SDR receivers is IFSS, that's interference-free signal strength. That's testing for receive IMD products, and also NPR. It's an old noise power ratio test used in analog systems, but it's adapted to stress test SDRs. What's extremely important in an SDR is the purity of the master clock used in the A to D chip, or the ADC chip, that it's got to be ultra clean. That means the power supply feeding it's got to be ultra clean. So that's where the weighting is going to go in to provide a really super clean clock signal, because that causes problems if you've got noise on there. And also testing at that point, because we're getting better and better quality performance from an SDR. A lot of the traditional test equipment, its phase noise and its power supply is not that clean, and they're going to have problems, getting down and really measuring how low these things can go. Overloading of an A to D converter chip is a thing we want to avoid at all costs, and there's a lot of ways that this is done in a SDR. So there can be gain control in multiple stages there to be sure that we're never going to overload an A to D. Now, purely if you overloaded an A to D, garbage would come out, and it would be a horrible, terrible sounding digital bit stream of abject garbage noise. But then again, you're never going to see that happen in a modern transceiver. And you can have an overload indication that you're getting close to it, it's starting to happen. But truthfully, at that point, at that little knife's edge of it getting a little overloading, those are really what we call soft overloading. And it can handle a little bit of momentary overload because it's very sporadic. It's not all together at the same time. So it doesn't go down the drain as fast as one might think. One thing that most manufacturers are implementing is bandpass filtering in front of the A to D converter IC. And, this is just going to keep out all kind of loud, erroneous signals from getting in and blending and mixing because, you still have opportunities for IMD products and mixing of incoming signals that are happening, outside of the chain. So you want to be sure that that AM station down the block that's running 10 kW that your receiver's looking at doesn't get in and start to cause havoc. Now, I mentioned earlier about expanding the dynamic range of a to D converter chip, and two types of things are done. First thing I want to mention is dithering. And basically, you're still going to have mixing products occur and use possibility of seeing spurious signals on the waterfall and hearing stuff that's not really there. So dithering is often used. You're going to see a switch for that, say, on an ICOM 7300, 7610, and most times it's part of the A to D chip itself. It offers a dithering option. What dithering is adding noise to the incoming signal. And it sounds sort of crazy to add noise to an incoming signal, but why would you do that? Well, what happens is the random noise that you're mixing in, sort of custom tailored noise, is mixing with these spurious signals at particular frequencies and blending them out to random noise. It's making them random. It randomizes them. So basically what happens is you're cleaning up the receiver in general, but you are bringing up the base noise level of the receiver because those spurs turn into white noise basically in the passband of the receiver. So the noise floor can start to come up. And of course that's a trade-off because you can start to gain 5-10 dB of dynamic range by adding this dithering, but you're also going to bring up the noise floor. What is really in consideration is real world situations of an actual operator because most people don't live out in a RF vacuum. I know I'm in a suburban environment here and I have got junk from TVs and all kind of noises and grinding noise. The noise floor just comes up from overnight. As long as things like this increased noise floor is not above your local noise level, you're not going to ever deal with it. So you can afford to put a little dither in there because most people's background noise level is not zero. The other thing that's done is decimation, and that's done in really the nice higher class radios, and that is where the sampling occurs at a much faster rate than it really needs to happen to get high-quality digital representation of the signal. So decimation, like I said, by pretty much oversampling, allows us to digitize our signal at a very high sampling rate. And at that point, you'll end up increasing the dynamic range, create what's called processing gain. And that means that the dynamic range is increased in its number of dB by the processing gain of oversampling and then bringing it back down to a usable level. One of the last things I'd like to mention is latency. And that is, I think we're seeing a lot of that on the news lately, aren't we? But latency is the propagation delay of the signal from RF to AF through the system. In other words, the computer and all the stuff that's in there, the gate array and everything has to do this processing, and it's going to take X amount of time. It's going to take a certain amount of time. And generally in the world, we consider under 150 milliseconds to be somewhat real time, but you don't want to have a ton of latency in there. And so when bandpass filters are created mathematically and done in DSP chips on an SDR, we have to sort of decide how tight do you really want those skirts, because if you want a brick wall filter, you're going to have to incur some latency because it takes longer to do the processing. So it's just another, always a compromise, balancing act between what you want, what you'd like to get, and some trade-off. In this case, it's filter skirt brick wall tightness versus latency through these filters in the DSP chip. The whole balancing act when you're doing an SDR design includes these items. Well, how expensive an ADD chip do you want to put in the radio? What price class is it at? The latency, again, how tight those filter skirts are. How many bits is your system going to operate at? That's going to be dictating your dynamic range. The radio size, what size is it? How many knobs are you going to have on it? What is the display size and resolution going to be? And in the firmware for it, how many of the DSP filter types are you going to implement? Well, I hope that was of some value to you. Now let's get back to reviewing this great new G-90 SDR. The G-90 is using the Cirrus Logic 24-bit chip, which is much lower sampling frequency than the direct sampling chips used in the multi-$1,000 radios. Those chips cost hundreds of dollars just for the IC. But don't think for a minute you can't get great performance out of a mixer, and the G-90 is certainly a shining example of that. Although there's no circuit design diagrams available, we're going to take a look at the chips inside and see what we can discern from what ICs they're using. Well, take a look at the filtering section of the main circuit board. We've got 30 relays because we have an automatic antenna tuner, we have the low-pass output filters, and we have receive preselection filters. Now, looking at the size of the toroids, they look absolutely appropriate for dealing with these power levels. You can literally hear the filters on the preselection filters switching in and out as you tune across the band, and it seems like they switch about every 100 kilohertz on, say, 20 meters. The G-90 uses an ARM 32-bit microprocessor. It must be doing the user interface and the number crunching, and it's certainly up to the job. The final amplifier uses a pair of Mitsubishi RD16 HHF transistors driven by an RD06 HHF. The transformer used with them looks appropriately sized, and these are the same family that are used in the FTDX101 Delta. These are rated at 16 watts out typical, with a max of 20 watts out, up to 10 meters with 12.5 volts running them. Now, they're fed with the 06 HHF transistor. It's capable of 6 watts, but it only requires about 0.05 watts to tickle these finals to full output. That means that they're running way in their linear range, and if heat synced properly, these devices could be happy to run well over 16 watts out each. The standby current is about a half an amp each on these, and this overall efficiency is 65%. They're also SWR protected up to 20 to 1. And they can handle a maximum VCC voltage of 15.2 volts. I'll show you something interesting. We're used to radios dropping their power level or tracking their power level output on the transmitter when your VCC, your voltage coming into them, goes down and up. So 13.8 volts will produce that solid full power rating, but as we go down from that, say if you're on batteries, the output power will go down. Not the case with the G-90 here. I'm running it at, what are we showing right now, 13.8. Keyed up, roughly 18 watts out or so. This meter's not very accurate at the old, it's an old meter and it's at the bottom end of its scale. There's 13 volts, same power out. 12.5 volts, same power out. 11.9 volts, same power out. 11.2 volts, same power out. Wow, this is getting crazy here. 10.6 volts, same power out. 10.4 volts, same power out. This means you could run lead-acid batteries or your lithium polymers all the way till they're completely discharged and get the same power output, and the radio's going to function. That is great. Receive current draw on the G-90 is about 650 mA, typical for an SDR with a display screen like this. Transmit current draw, about 8 amps absolute maximum. Now the power cord's a little light for my taste, so what I did was right past the fuse, I cut it in half since it was quite long and doubled up on the wire and brought it out to an Anderson power pole. I also added a little ferrite like they suggest right next to the connector. The first thing you'll notice is it's got some weight to it because the case is made out of really good thick metal stock, and the front and back handles really give it a polished look. The LCD is the next thing you notice. It's small, but it does a nice job of providing all pertinent information. What's most important is that the spectral display and waterfall is a very fast refresh. I'd say it's at least 20 hertz. Now, it's fixed at 48 kilohertz, plus and minus almost 25 kilohertz, but that's where all my other SDR receivers stay anyway. That's the best bandwidth to look at. Now, there are a dozen function buttons, and all of them have multiple uses. The function key selects the secondary function, and a long press is also used to access other secondary functions. And all three rotary knobs press inwards for additional control. The main tuning knob is plastic, but I've seen other knobs on other radios that are about the same, and it is an area for possible upgrading. Once you power up and start tuning around, you find that the 24-bit receiver has a really nice sound to it.
Xiegu Europe from California, kilowatt 6, Yankee Radio Alpha, kilowatt
58 in Toronto, 5 and 8 in Toronto. My name is Mirek or Miras Slash QSL.
Nice signal coming out of Idaho. Joel, 5 by 9, 5 by 9. Let me not hold you. Enjoy your day and thanks for the shout.
Now remember how I said that if you want super tight skirts in an SDR, you have to incur more processing and a delay between the time the RF is actually on the air and it comes out of your speaker. These filters seem, well, a little softer than the super tight ones I've seen, but their ultimate selectivity is excellent, and the latency of the radio is very low, I'd say under 100 milliseconds. The G-90 remembers your settings for each mode, and shortwave listening is really a pleasure too, with the 5.5 kilohertz bandwidth set. It's about 5400, with 100 cycles on the bottom end. And the display works quite well when you're working with AM stations on shortwave. It's easy to memorize the channels too. All you do is tune it in on the VFO where you want. You have VFO memory button here, tune it in where you want, hit the memory button once, and you'll see the channel button number blinking. If it's blank, it'll tell you that it's blank, and hit the MW again, and it puts it right into the memory. I'm going to back out by just hitting the main tuning dial in. Switch between memories and VFO, quite easy. You can go up and down as well on the microphone from here. It's WWV. Very nice. The G-90 has two digital data communications ports, one on the head here, which reportedly can be used for CAT control as well as firmware updates of the head unit, and one on the rear here, which is currently used to update the firmware on the main radio's body. Xiegu provides the firmware and the programming package on their website. Although the G-90 does not provide a USB connection for audio device output, the analog audio in and out is available on the accessory connector, as well as PTT and output voltage control for switching bands on an external amplifier. Circuit board layout and construction looks to be pretty much state-of-the-art, typical of what you'd find in any of the major amateur radio manufacturers' equipment. Xiegu claims their next product offering is going to be a remote control head for the G-90. It's going to have a 5-inch display and enable other functions in the radio, like FM. Xiegu already offers the XPA-125B linear amplifier, which mates up with this radio nicely. It has finals in it which are rated quite a bit higher than 125 watts, and so it's really loafing and delivers average power in SSB about 50% higher than you'd see on a 100-watt radio. This amp also includes a wide-range antenna tuner. The G-90's internal antenna tuner is much more like the antenna tuners from radios of a few years ago, and that's a good thing, because the recent crop of automatic antenna tuners in rigs will not tune unresonant antennas past about a 3-to-1 SWR. Now, I don't know the ultimate range of this tuner, but it quickly tunes up my 40-meter folded dipole on all the bands above 40. So here we're on 15 meters. Let's hit the tune button. Oh, got 15 meters. Go down to 18 megahertz. And it's tuned. So it is a very wide-range antenna tuner, and it's darn fast. Now, because the radio doesn't have a broadcast band filter, a lot of times, even on a resonant antenna, I will like to leave the antenna tuner in. say on 20 meters here with my hex beam, because it adds another level of protection to the radio's front end. Adding a broadcast band pre-filter on the receiver is on my suggestions list sent to the Xiegu engineers, and I'm also working with Pacific Antennas on a small low-cost external add-on filter. The G-90 decodes CW pretty darn well, or as good as most rigs I've seen. You tune the tuning dial until you see the yellow LED blinking, and it seems that adjusting the key speed of your sending actually has an effect on the receive accuracy. When you're wanting to tune around, the highlighted digit is the digit that the main tuning dial is going to tune. Now, in this case, 1 kilohertz. As you press it in, it increments through single cycles, tens, 1 kilohertz, and 10 kilohertz movements. So on SSB, you'd probably be in the 1 kilohertz movement. A lot of people land up on even frequencies. Remember, if you need to move to the next digit, you hit it 3 times, and you're in the next lowest one. Increment up 1, hit it 3 times, you're on the next lower one. Now, before we listen around on the bands, let's list what the radio has. It has dual VFOs and 63 memories. It's got an AGC with a slow, fast, and auto setting. It's got the multifunction knob that does a lot of stuff you want to do with it. It's got completely variable digital RX bandpass filters and a TX microphone compressor. It also has an auto antenna tuner that I find to be very wide range and an SWR plotter. And it's a full spectrum HF receiver, 500 to 30 megs. It's got a very fast FFT spectrum and waterfall display. It does CW break-in, and it has a CW decoder. The removable head comes off, and they provide a DB9 connector cable. It is 20 watts. That's a big deal. And the firmware is upgradable by the owner, and they give you the firmware programming cable too. Now, it doesn't have digital noise reduction or a notch filter, and the noise blanker, well, it's more like a noise gate, but they are revising the firmware pretty often.
Mexican restaurant. Oh, 2 questions. Did you get any information on Xiegu Europe from California, kilowatt 6, Yankee Radio Alpha, kilowatt. The antenna is the same old TH7, 7-element Yagi. That's it there. Anyways, he looks like...
The last letter Sierra. Kilo 8, Whiskey Romeo Sierra. QSL? Okay, good luck to you. This is Whiskey for America.
Whiskey 4, Sierra Romeo November.
Whiskey 2, United
The
4 Sierra Romeo November.
North America, secure stateside. IK6 BGJ, secure North American body, over.
And there's a good example of a signal right under us that's pretty darn strong. His top end is in our passband, but this radio seems to have very tight ultimate
sorry,
skirts.
I have a voice on my receiver, but I can't read because of the QRP. Would you please repeat your call, please, over?
This radio is somewhat in a new niche because I can tell you that all of my other QRP radios that run 5 to 10 watts, 90% of the time I cannot snag another station in SSB mode. They just cannot hear me. And I'm out on an island or whatever, if I'm running digital or CW, it's a fine power level. But without an additional power amp to bring you up that little bit extra, you're going to have a rough time on SSB when you're out in the field. The current draw on receive on this SDR is about 650 mA, and that's quite a bit more than you would have on a typical very simple QRP field radio. But luckily with our new lithium batteries, that's not going to be too much of an issue. As well, this running 20 watts, 90% of the time I can snag the other station in sideband because my average power levels are twice that amount. And if you do a test with a friend with a 100-watt radio and go, okay, lower your power 75, 50, 25, every time I've done that under normal conditions, I can't tell any difference, almost no difference in the meter reading till they go to 25 and start dropping under that. So really, there is a tremendous difference between average SSB power levels at a 5 to 10 watt radio and a 20 watt radio. And this really does deliver 20 watts. That is a huge difference. Now, Xiegu, they're a very small business. They're new into the ham radio arena. They do seem to want to establish themselves as a more of a presence and a solid, reliable company. So you can watch videos of their factory and that stuff online if you want to. I don't think that there is a U.S. repair facility yet. That may be evolving as I speak, but I don't believe there is one. You'd be swapping out equipment. But as you know, if a radio works and you run it through its paces for a week or so, and if it's all working, it will tend to stay working. You know, the solid state stuff is just like that. So if you do buy stuff like this now, you are an early adopter. You know I am, and that's why I bring these new products to you, but you are taking a slight bit of a risk. Now, on the plus side, what you get is a tremendous value and a lot of, unique little aspects to the design of this radio. It's coming from a sort of different mindset over there in China. So I hope this helps you figure out whether the G-90 is a fit in your shack. So until next time, take care. The authorized U.S. dealer for the G-90 is RadioOddity.com. They've got support and the best price.